Okay, so this is the review for calculus, our upcoming exam. I thought I would go over the review sheet that I gave you, just two quick notes, or rather one quick note. There were two problems that we didn't go over and we won't go over for the semester. Those are problems 3 and problems 9. So I've omitted them from this review because you're not expected to know that material. Okay, so let's begin here. F of 4 is equal to 9. 1 is less than or equal to f prime of x for x in this range. How small can f of 11 be? Well, oops, what did I do there? Just a moment. Okay. Well, we're going to use this nice fact. We know that for any function which is continuous on its domain, we have this fact. F of b minus f of a all over b minus a. There exists some c in this range from a to b such that f of b minus f of a all over b minus a is equal to f prime of c. Took me a minute to get my bearings there, but okay, that's the theorem that we're going to use. So in this case, we know that there's going to be some value c such that f of 11 minus f of 4 all over 11 minus 4 is equal to f prime of c. Okay, wait, stop. We know that f prime of c, what's the smallest value for f prime of c? It's 1, right? We know that from this fact here. So that means that this whole thing here is less than or equal to 1, is greater than or equal to 1, rather. Okay, fine. So what is this equal to? So this is saying 1 is less than or equal to f of 11. I don't know what value that's going to be. I'm figuring out how small it could possibly be. So f of 11 minus f of 4 is 9 all over 5. Okay, so now I'm going to solve for this inequality. I'm going to say that this is, I'm going to multiply by 5 on both sides, so I get f of 11 minus 9 is greater than 5, greater than or equal to 5. And so that tells me that once I add 9 on both sides, I get 14 is less than or equal to f of 11. Good. So that's going to be our final answer. All right, good. Next, I have this question here. Given the function f of x, graph it following these steps. So first step is state the domain. What's the domain of this function? Well, I know that the domain is wherever x minus 4 is not equal to 0. So that's telling me that x cannot be equal to 4. If you want to put in interval notation, you could say the domain is from minus infinity to 4 union 4 to infinity. Okay, and you would box that. Make sure to box all of your answers on the exam, and you get full credit. Find the x and y intercepts. The x and y intercepts. So for the x-intercept, that's when y is equal to 0. And that tells me, okay, so if y is equal to 0, that tells me x over x minus 4 equals 0. That tells me x equals 0. So 0, 0 is the x-intercept. For the y-intercept, that's when x is equal to 0. It's always the opposite of what you'd expect. So for the y-intercept, x equals 0. For the x-intercept, y equals 0. Okay, fine. So that means I just plug in 0 for my f. So that's 0 over 0 minus 4. And again, I get 0. So the x-intercept is the y-intercept, is the origin is 0, 0. Good. State whether the function is symmetric. Well, this function is neither even nor odd. No symmetries. Okay. State the asymptotes. Okay, well, there are going to be two types of asymptotes, vertical asymptotes. And the vertical asymptote I know occurs when the denominator is 0. So I know there's going to be a vertical asymptote at x equals 4. Horizontal asymptote, well, let's see. Horizontal asymptote, in this case, is going to be at y equals 1. Why? Because here there's a 1, here there's a 1. These both have the same degrees. They're both degree 1 polynomials. And so in that case, we just take the ratio of the leading coefficients, and that's going to be just 1 over 1, which is 1. Good. State the intervals of increase and decrease. Actually, this is going to take some doing. So let me just box the answers here, and I'm going to move on to a blank slide. So we're supposed to find the intervals of increase and decrease. So my function is f of x equals x minus 4. Oops. F of x equals x over x minus 4. There we go. And I want to find the derivative. So I know the derivative will be g f prime minus f g prime all over g squared. Here my f is x. That means f prime is 1. My g is x minus 4. So my g prime is also 1. So that's telling me that g f prime, that's going to be x minus 4 times 1 is just x minus 4, minus f g prime, which is just x, all over g squared. So it's x minus 4 squared. These x's will cancel, and I'm left with minus 4 all over x minus 4 squared is my f prime. Okay. Well, the question was asking us, what was the question asking? It was asking us to find the intervals of increase and decrease. In order to do that, you set this equal to 0, and then you draw your number line. But the thing is, if I set this equal to 0 and solve, I get minus 4 equals 0. That's impossible, right? So that means that actually there are no critical values. And so to find the intervals of increase and decrease, I'm not going to map any other functions other than where I have a discontinuity, where I have a vertical asymptote. So that's going to be at the point 4. So the only point I'm mapping here is at 4, which is a vertical asymptote. The function is not defined at 4. So let me just explain why you do this. So the function can go from increasing to decreasing at a vertical asymptote, right? So here it's increasing, let's say, and then on the right of this asymptote, it's decreasing. So that's why I'm going to check the values to the left and to the right of 4. Remember that my f prime is minus 4 over x minus 4 squared. I'm going to plug in values to the left and to the right of that. So to the left, if I plug in, let's say, minus 100, I get negative over positive is a negative number. To the right, if I plug in 100, let's say, again, I get a negative over a positive. A square is always going to be a positive, right? So I get a positive here. Sorry, I get a negative. A square is always going to be a positive, so negative over positive is negative. Good. So actually, where is the function increasing? It's never increasing. So I write the empty set. And where is it decreasing? It's decreasing from minus infinity to 4, union 4 to infinity. Good. Let me actually just box the whole thing. So that'll be our answer for number E. Good. Okay. The next questions say, state, oops, this is a typo, sorry. Find the local maximums and minimums. So to find the local maximums, we have to look here, right? Since the function is always decreasing, there are going to be no local minimums or maximums. Remember, a maximum and a minimum occur when the function goes from being positive, where the derivative goes from being negative to positive or positive to negative, right? So a minimum looks like this. The derivative is negative and then it becomes positive. And a maximum looks like this. Derivative is positive, and then it becomes negative. So since that's never going to happen, since the function is always decreasing, we're actually never going to have any maximums or minimums. Okay, so state the inflection points. Inflection points occur when the second derivative goes from being negative to negative or positive to positive. So I'm going to take the second derivative now. My f prime of x, remember, is minus 4 all over x minus 4 squared. So to find the second derivative, I'm going to do gf prime minus fg prime all over g squared. So my f is minus 4, oops, minus 4. F prime is 0. G is x minus 4 squared. And g prime is, let's see, it's going to be 2 times x minus 4 times, so derivative of the outside times derivative of the inside. Derivative of the inside is just 1. So that means that this whole thing here is going to be g, f prime is 0, so I'm not going to write that, minus f g prime, and that's going to be minus negative 4 times 2 x minus 4 all over g squared. So that's going to be x minus 4 to the 4th power. So x minus 4 squared, maybe I won't skip any steps. And you can simplify this. This is going to be 8 times x minus 4 all over x minus 4 to the 4th power, which is 8 over x minus 4 cubed, because you can cancel this with this, and this becomes a 3. Good. Very good. Okay, so what was the point of doing all this? It was to find the inflection points. So let me actually do that here. I know that f double prime of x is 8 over x minus 4 cubed, and I want to find the inflection points. Well, points of inflection occur, I'm going to set this equal to 0, and I find that this is equal to 0 if and only if 8 is equal to 0. But that's a contradiction. So as a matter of fact, there are going to be no inflection points. No inflection points. No points of inflection. Very good. Okay. Final question was to graph the function. I'm just going to make this smaller. And I'm going to graph the function here. So what do we know? We know we have a horizontal asymptote at 1. Okay. And I know I have a vertical asymptote at 4. Okay. And I know I have my x and y intercept is the same, it's the origin. And I know that the function is decreasing everywhere. So if it's decreasing and I need to follow my asymptotes, it'll actually look like this. Okay, it actually looks like this. It has to, because it's decreasing. And to the right here, I have two options, right? So it could either be this, or it could either be this. But if it's this second one, it can't be the second one, because the function's decreasing everywhere. This guy here is decreasing. This guy here is increasing. So I can't draw that. It has to look like this. So that's actually the final answer. That's what our function looks like. Good. Okay, so that was number 1 and 2. We said we were going to skip 3 because that's material that you're not responsible for. So let's go on to number 4. Find two numbers whose sum is 64 and whose product is maximal. Well, we did examples like this in class. Two numbers whose sum is 64. You know, we give these a name. So I'm going to name them x plus y, and we know that x and y, so x plus y is 64. And we want to maximize their product. I want to maximize their product. Well, okay. If I want to maximize this, I have to take the derivative and set it equal to 0, because remember, when you have some function its maximum occurs when x equals 0. Incidentally, the minimums also occur when the derivative is 0. Sorry. I think I misspoke. The maximums occur when the derivative is 0, and the minimums also occur when the derivative is 0. Okay, hopefully I said that clearly. Okay, so I want to maximize this function. I have to take the derivative and set it equal to 0. Well, the problem is I can't really take the derivative when it's in this form, so I'm going to solve for y in terms of x. Y is equal to 64 minus x. And then I'm going to plug that in. For y. I'm going to substitute for y. So this becomes x times 64 minus x. That's equal to 64x minus x squared. And this I can take the derivative of. So derivative of this, forgot this x here. Derivative of this is 64 minus 2x, and we set that equal to 0. If you solve this, you get 2x equals to 64, x equals 32. Okay, so if x is equal to 32, and I know that x plus y equals 64, so this tells me 32 plus y equals 64. This tells me y equals 32 as well. And so the two numbers are going to be 32 and 32. X and y are equal. They're equal to 32. That's going to maximize the product. And you can check that. You can check that by plugging in numbers, and you'll see that generally that's the correct answer. All right. Of course, plugging in various numbers, that's not a proof. Nonetheless, it's a good sanity check. The sum of two positive, now we're on to B, so the sum of two positive numbers is 36. I'm going to write that down. X plus y equals to 36. I'm going to keep in mind that these are positive numbers. That's going to come in, that's going to be useful later. So x plus y equals 36. What is the smallest possible value for the sum of their squares? So I want to minimize x squared plus y squared. Well, okay, same trick as before. I want to minimize this, so I have to take its derivative, right? But I can't take the derivative currently. Or I could use implicit differentiation, but that's a big headache. There's a simpler way to do it. You could just say, okay, x plus y equals 36. That tells me y equals 36 minus x. You could solve for either x or y. It doesn't matter. In this case, I think it's just easier to work with x. Okay. Or rather, it's clearer to work with x. So this tells me that this is equal to x squared plus 36 minus x squared. And this is equal to x squared plus, let's see, I'm just looking at my notes here. 36 squared is 1296. Minus 72x plus x squared. So if you're wondering what happened, I just expanded this out. Okay. Actually, let me make a new slide here. Let me make a new blank slide. Very good. Okay, so here we are. I'm going to rewrite all of that. Just a moment here. So x squared plus y squared was x squared plus, what was it? 36 minus x squared. And this was x squared plus 1296 minus 72x plus x squared. And if you simplify this, combine like terms, you get 2x squared minus 72x plus 1296. Good. And now we just take the derivative of this. So let's take the derivative. And we set it equal to 0, so this becomes 4x minus 72 equals 0. 4x equals 72. The arithmetic is very easy. And so that tells me that x is equal to 18. And if x is equal to 18, remember that x plus y is 36. So that's telling me 18 plus y equals 36. That tells me y is equal to 18. So y equals 18 and x equals 18. Those are our solutions. That's going to minimize the sum of the squares. The sum of the squares of these two numbers is going to be minimal when x and y are equal to 18. Good. And again, you could do a sanity check. You could just plug in various numbers and see that that's correct. Excellent, good. So find the points on the curve y equals the square root of x closest to 4, 0. I love this question. These are the most fun questions. So I'm going to draw a picture. So here's y equals square root of x, and here's the point, let's say 4, 0. I want to find the point that is closest to this point. So, here's 4, 2. I think the point that's closest is probably going to be a little bit to the left of 4, 2. But let's see. So we want to minimize. So remember, there's the distance formula. We went over this in class. The distance formula is x2 minus x1 squared plus y2 minus y1 squared. And instead of minimizing the distance, we're going to minimize the square of the distance. It turns out that that's equivalent. If you minimize the square of the distance, you minimize the distance. Hopefully that's intuitive. Okay, good. All right, so what's my x and what's my y in this case? In this case, my x is 4 and my y is 0, so I'm just going to plug that in. D squared is equal to 4 minus x squared plus 0 minus y squared. Good. And what's my y equal to in terms of x? Well, since I'm on this curve, since this red point that I'm looking for is on this curve, its x and y values will obey this equality, so I can actually just plug in. I'm going to keep 4 minus x squared, but I'm going to say, okay, 0 minus y, what is y? Y is just the square root of x. So this is 0 minus the square root of x squared. Okay. Good. And now I'm just going to minimize this. I want to minimize this. So first I'm going to expand this out, and then I'm going to take the derivative, set it equals 0, and then I'll have found the minimum. Okay, good. So let's expand this out. This becomes 16 minus 8x plus x squared plus, so let's see, 0 minus the square root of x is just negative square root of x squared. That would typically be the absolute value of x, square root of x. So let me just write a note here. Square root of x squared is actually the absolute value of x. But since I know x is positive, right? X has to be positive since it's on this graph. It's just gonna be x. So this is plus x. All right, good. So this became plus x. And this is equal to 16 minus 7x plus x squared. Now I'm going to take the derivative of this whole thing and set it equal to 0. So derivative is minus 7 plus 2x equals 0. And that tells me 2x equals 7. X equals 7 over 2. So the point closest to this point on this curve is going to be 7 over 2, comma, square root of 7 over 2. That's going to be the answer. And actually, if you take a look, 7 over 2 is a little less than 4. 7 over 2 is going to be exactly, yeah, it's exactly going to be this point, right? Just sort of like our intuition told us. Okay, excellent. Very good. Very good. Okay. Find the intervals of increase and decrease. I'm just going to do A. I'm going to leave B for you. These questions are relatively simple, I think. So to find the intervals of increase and decrease, we take the derivative. We set it equal to 0, and we can plug in numbers to the left and to the right. We can use second derivative test. I'm going to do just plugging in numbers to the left and to the right, because in a subsequent question, we're going to be using the second derivative test. So I want you to see both methods. Okay. Taking the derivative here, I get 9 plus 3x squared plus 2x cubed equals 0. I'm gonna set that equal to 0. So this is 6x plus 6x squared equals 0. Factoring at 6x, 1 plus x equals 0. And so the critical values are going to be x equals 0 and x equals minus 1. Let's map that onto our number line. Here's minus 1, here's 0. F prime of x, remember, is 6x times 1 plus x. Let's plug in values to the left and to the right of these critical values. So to the left of minus 1, let's pick minus 100. That's going to be positive, negative, negative. And that's positive. Okay. Between minus 1 and 0, let's pick minus a half. So that's going to be positive, negative, positive. That's negative. To the right of 0, let's pick 100. That's all positive. So that's positive. Finally, the answer is intervals of increase are from minus infinity to minus 1. Oops. And union, sorry, I almost forgot. Union from 0 to infinity. Okay. And our intervals of decrease are just from minus 1 to 0. And that's the answer. Good. Like I said, I'm going to skip B here. All right. Find the number c which satisfies the mean value theorem for this function on this interval. Good. So we know that the mean value theorem says that f of 2 minus f of 0 all over 2 minus 0. There's going to be some c between 0 and 2 that satisfies this. So there exists a c such that this holds. Okay, good. Let me just check my notes here. Give me a quick minute. Where did my question 7 go? Sorry about this. Here it is. Okay, so f of 0, if you plug it in, is 1. If you plug in f of 3, what do you get? I'm not going to plug in the numbers. I know you know how to do that. That's going to, sorry. If you plug in f of 2, that's going to be 3. So this is 3 minus 1 all over 2 minus 0, which is 2 over 2, which is equal to 1. So now we just take the derivative of this function, and we set it equal to 1, and we solve. So this tells me that 4x minus 3 equals 1, 4x equals 4. That tells me x equals to 1. And what do you know? X is between 0 and 2 in this case. So the answer is x equals 1. That is rather, c is equal to 1. Doesn't matter. If you wrote x equals 1 on the exam, I wouldn't take any points off, but let's just be clear. So the value c, which is guaranteed by the mean value theorem, is equal to 1. Good. Find the absolute maximum and minimum of this function. Okay, that's doable. This is very easy. Okay, let's see here. Now I'm looking for my question 8. That's odd. Here it is. Here it is. Good. Okay, so first of all, we know that maximums and minimums occur, local maximums and minimums occur when the derivative is equal to 0. So I'm going to set the derivative here equal to 0. Again, minus 2x equals 2. So that tells me x is equal to minus 1. Okay, so now I'm going to plug in f of minus 1, but I'm also going to plug in these endpoints here, f of minus 3 and f of 4. And that's going to be, let's see, minus 3 is, f of minus 3 is minus 4. If you plug it into the original function, this function, you get minus 4. If you plug in f of 4, you get minus 25, and f of minus 1 is actually equal to 0. Okay, good. So to find the maximum occurs at, it looks like, minus 1 comma 0, because that's the highest y value, is 0. The minimum occurs at 4 comma minus 25, because that is the smallest of all these values. Okay, so those are going to be our answers. Good. All right. Number 9 we skip. Like I told you, you're not responsible for that material. Using the second derivative test, find the local maximum and local minimums of this function. Okay, fine. So let's recall the second derivative test. It says that if f double prime of x is positive, x is a max. Oh, sorry. X is a min. Got that wrong. And if f double prime of x is negative, x is a max. It's always the opposite of what you'd expect it to be. All right, so I'm going to take the derivative here. That's going to be, so f prime of x is 24x plus 24x squared. And I'm going to set that equal to 0 so I can find our critical values. Okay, so critical values, let's see. I'm going to factor out 24x, and I get 1 plus x here equals 0. So that tells me x equals 0 is a critical value, and x equals minus 1 is a critical value. Okay, I could, typically we just map these on the number line, and we plug in values to the left and to the right. But this time, let's use the second derivative test. So second derivative is 24 plus 48x. All right, now let's just plug in our critical values. F of 0 is 24, which is positive. That tells me 0 is a min, okay, since it's positive. F double prime of minus 1 is, let's see, 24 plus 48 times minus 1. That's equal to minus 24. That's negative, and so that tells me that minus 1 is a max. Okay, so 0 is a min, and minus 1 is a maximum. Okay, so that does it for our review. I'm sure that you guys will do well on the third exam. You did well in the first exam, you did well in the second exam. So I really have no doubts about the upcoming exam, and then of course the final, the departmental final. Thank you very much. Your exam, remember, is on December 4th after the Thanksgiving break. So I will see you when I return on the 10th. I'll see you then. Thank you.